This is worksheet 6. We're going to be solving worksheet 6 and going through it. 1 second. All right, worksheet 6. Problem 1 says, what is the speed of sound in air at 45 degrees C? All right, 45 degrees C. First of all, we need to solve for the degrees in Kelvin. So 45 degrees C plus 273 degrees C, and that's going to give me my Kelvin. It's going to be 318 Kelvin. And then to solve for the velocity of the speed of sound in air, V equals 20.1 times the square root of 318 Kelvin. So the formula is V in air equals 20.1 times the square root of the temperature in Kelvin. All right, and so for that value, we get 358.43 meters per second. What is the wavelength of the note A, 440 hertz, at this temperature? Okay, so for this, we're going to use our wave equation. V, the speed of the wave, equals F, the frequency, times lambda, the wavelength. So we'll go ahead and use 358.43 meters per second equals 440 hertz. That's given by the problem. And hertz is a unit that is the same as 1/2 times lambda. So now lambda will be equal to 0.81 meter. Okay. And what is the speed of sound in helium at 45 degrees C? All right, that's a different, same equation, different coefficient. Okay, this is 1C, 1-C. So this is going to be equal to 58.8 V in helium times the square root of the temperature in Kelvin. So that's going to be 58.8 times the square root of 318 K. And this is going to be equal to 1048.55 meters per second. And by the way, this is why when you suck in the helium from one of those balloons you get at the 99-cent store, your voice sounds high because the sound is faster. And since the wavelength is going to be the same because it's a function of your instrument, your vocal instrument, we're going to have a higher frequency, and frequency is going to determine the pitch of the sound. So go ahead, buy some balloons and check it out. It's kind of silly, it's kind of crazy, it's kind of fun. Little zany thing to do, and it won't hurt you. Little clean fun that won't hurt you. All right, that was 1. Now number 2. Problem 2 states a satellite experience at 300 kilometers experiences air resistance and re-enters Earth's atmosphere. As it moves downward, the frictional force of air resistance is converted into internal energy or heat. If the satellite is made of aluminum and all of its kinetic energy is converted into internal energy, what would the temperature increase be? Okay. Let's see. So we're given some quantities. We're given the mass of the satellite equals 1 kilogram, and C of aluminum, the specific heat, is 890 joules per kilogram degree C. The mass of the Earth is 5.98 times 10 to the 24th kg. And the radius of Earth is going to be 6.35 times 10 to the 6 meters. All right. So the first thing we need to do is we need to find the velocity. Let's see. We need to use our handy dandy mv squared over r is going to be equal to g m1 m2 over r squared. So I'm looking for v. I'm going to take one of these, the mass of the satellite out, and I'm going to take one of these, will cancel with that. So V is going to be equal, and I believe we did a problem just like this in one of our other worksheets. Square root of G, mass of the Earth, over R. All right. So we're going to have R is going to be equal to this plus the radius of Earth. So it's this is 3 times 10 to the 5th meters. That's the equivalent here. I'm just going to add this. So V is going to equal to the square root. G is 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. And then that's times the mass of the Earth, 5.98, 10 to the 24th kg. And then that's over R, which is the radius of the Earth plus the height of the satellite above the Earth. So that's going to be 6.85. I'm adding, this is 5th right here. If I add that to the radius of the Earth, it's going to be 6.85 times 10 to the 6 meters. And V is going to be, let me write it down here, and I'll 7744.7 meters per second. Okay, give myself a little more space now. All righty. We got V. Now we're going to determine what the heat will be, the change in heat. Okay, so let me get that. Okay, so we're going to have the conservation of energy says that everything is going to be turned into internal energy. So Q is going to be equal to 1/2 mv squared. So Q, remember, we don't have an expression or a value for Q, but we do have an expression for it. We have Cm delta T equals 1/2 mv squared, and the m's go. Interesting that mass cancels out again, and I want to know what delta T is. So delta T is going to be equal to v squared over 2c. Yeah, so it's going to be equal to 1/2 times 77447 meters per second quantity squared divided by 890 joules per kilogram degree C. And we're going to get a delta T to be 33696.5 degrees C. And that would certainly burn up on entrance to the atmosphere. All right, that was number 2. All right, number 3 reads, a swimming pool has dimensions 10 feet by 10 feet by 8 feet. So it's 10 feet by 20 feet. I'm sorry, by 20 feet by 8 feet. What is the gauge pressure at the bottom of the pool? So it's 8 feet is the depth. So the pressure is going to be rho GH. And we're going to get rho of water. So we're assuming that it's just normal water, not salt water. Is going to be 62.4 pounds per foot cubed. And I know I said we wouldn't work in anything but SI units, but we do in pressure. So we're going to have 62.4 pounds per foot cubed. And this is rho G. This is actually gamma. So this already has the G in there, right? Because we see we have a unit of pounds, not slugs. So, and then times 8 feet. And that's going to be 499.2 pounds per foot squared. And then that's the gauge pressure. In order to find the absolute pressure, I'm going to have to add atmospheric pressure to that. But my knowledge of atmosphere is 14.7 psi. And I can't this unit, pounds per square inch, and feet, pounds per foot, square foot, won't really mesh. So what I'm going to have to do is I'm going to have to convert this. Well, that's what I did in the solutions. I could convert either one. But here in the solutions, let's just stick with what we did here. 499.2 pounds per foot squared. And I'm going to go ahead and do this in PSI. And then that's 1 foot squared over 144 inches squared. And you say, why 144? Because of the square, right? That's 12 squared. So we know that 1 foot is 12 inches, but 1 square foot is 144 inches. So this is going to be 3.46 psi. To get the absolute pressure, it's going to be 14.7 psi plus 3.46 psi. And that gives me 18.16 psi. And that is the pressure from the water, from 8 feet of water, and also from all that hundreds of feet or thousands of feet of atmosphere on top of it. Okay, so that was number 3. Number 4. Says a balloon is partially filled with air, sealed, and then warmed. What do you predict will happen to the balloon? I'm going to let you this to your pleasure, but I'll go ahead and read in case you don't have access to the solutions. It says the heating will cause the air molecules to move faster. They will hit the balloon harder, causing it to expand. Explain this from a microscopic point of view. You can, I already did that, so it says C above. What if the balloon is cooled instead? If cooled, the air molecules will move more slowly and hit the balloon with less force, and therefore it shrinks. Okay, number 5. Wow, I got my pencil turned fat all of a sudden. Let's see, how did that happen? Line width, I'm gonna go with, come on, that guy. Well, assume your mass is 70 kilograms, so 70 kg, and your neighbor's mass is 50 kg. Neighbor's is 50 kg. You are standing 2 meters apart. How much force do you exert on your neighbor? This is in Newton's law of universal gravitation. So Fg equals G m1 m2 over d squared. So that's going to be 6.67. This is G times 10 to the negative 11 newtons meters squared over kilograms squared. That's just G. And then times 70 kilograms, also times 50 kilograms. All right, that's M1 and M2. And then we're standing 2 meters apart. Very nice. 2 meters squared. And this is going to be 5.83 times 10 to the negative 8 newtons. That's what is the origin of the force? It's the gravitational attraction between two masses. Compare this force to your weight. Okay, what was I, 70 kilograms? All right, my weight is going to be equal to mg. So it's going to be equal to 70 kg times 9.8 meters per second squared. And that's going to be 636 newtons. So this was the attraction between me and my neighbor. And this is the attraction between me and the earth. And you can see that the attraction between me and the earth is much larger than that between me and the neighbor. Finally, it asks, what force does my neighbor exert on me? And that's equal but opposite. And that was problem 5. Okay, problem 6 reads, for a guitar string at a particular tension, the speed is constant and each pattern will have a different frequency. Assume the speed of the wave is 120 meters per second. So that would be V equals 120 meters per second. And lambda is the wavelength, is 0.8 meters. For the first pattern, the wavelength is 2 times the string length. What is the frequency? So we have the wavelength is 2 times the string length. So we have F equals, oh, wait a minute. Oh, well, let's see, the wavelength, F equals a V over lambda. I don't see why we needed the string length there. There might be a little bit. Oh, wait a minute. Assume the speed of the wave is 120. And we're going to just say, and let's correct that in number 6 to read, assume the speed of the wave is 120 meters per second, and the string length is 0.8 meters. So let's do it like that. So we'll be more consistent with the solutions here. So F equals V over lambda. So we know that V is 120 meters per second. And lambda is going to be 2 times the string length, which we corrected that, 0.8 meters. And we're going to get 75 hertz, or 75 over seconds. For the second pattern, the wavelength is the string length. What is the frequency? So all I have to do is take that 2 out, okay? And I'm going to get 150 hertz. So that's 150 hertz. All right, moving on. This is number 7. And it reads, one of your group members is standing at rest on a very slick ice pond. They then throw a baseball north with an acceleration of 30 meters per second squared. They are in contact with the baseball, so delta T equals 0.5 seconds. During the throw, the baseball's mass is 0.8 kilograms, M equals 0.8 kg. And your group member's mass is 60 kilograms. So mass BB, that's baseball, right? Basketball. Mass GM group member equals 60 kg. What is the force on the ball? So F equals MA. Do we know A? Let's see. Yes, we do. So F equals 0.8 kg times 30 meters per second squared. And that's going to be 24 newtons. What is the force on your group member? Well, by Newton's third law, it's going to be equal and opposite. Describe your group member's acceleration. Okay, so then we know the force is 24 newtons equals MA, and we know that 24 newtons equals 60 kg times A. So 24 divided by 60 kg and divide this side by 60 kg. I'll give me A, and that's going to be 0.4 meters per second squared. So that's my, the force is the same, however, the acceleration is going to be much less because my group member is much more massive than the baseball or basketball. Ooh, okay, so what is the ball's velocity? We have a velocity equals acceleration times time, right? VF equals V initial plus AT, but this is 0. So VF equals 30 meters per second squared times 0.5 seconds, and that's going to be 15 meters per second. What is your group member's velocity? Okay, so once again, we'll use that same equation. VF equals V initial plus acceleration times time. VF equals, this term drops out because it's 0. 0.4 meters per second squared times 0.5 seconds, and that's going to be 0.2 meters per second in the opposite direction. All right. Number 8 reads, a large truck breaks down on the highway and receives a push back into town by a small car. While moving at unchanged speed, does the car exert a force on the truck? Absolutely it does. Just the answer says, while it is true that the truck is not accelerating, and therefore the net force on the truck is 0, the car must exert a force on the truck equal to the force of friction. Does the truck exert a force on the car? Yes, by Newton's third law, it's going to be equal and opposite. Number nine is a fun problem. A fly lands, but you guys might not get it because I don't know if you know what an old record player is, but it's they had these things that were made out of plastic that you put on a turntable. Anyway, they were similar to CDs. A fly land, except they had a needle and grooves in them, on an old record player, while a 10-inch outer diameter, 33 RPM record is played. If the fly lands on the edge of the record, determine the magnitude and direction of the fly's acceleration. Well, we know that it's constant velocity, so that acceleration is going to be equal to v squared over r. All right, let's go ahead and do this. This is 10 inches, which makes r 5 inches. But I don't like inches, so let's go ahead and convert that into into meters. So 5 inches times 0.0254 meters per inch is going to give me 0.127 meters. All right, now I need to know V. I've got R, that's R. So V is going to be the time it takes to, the distance of the circumference plus the time it takes to get there. So V is going to be equal to circumference, which is going to be, it's 33 RPM. Let's 33 rev. Let's get the 1 minute over 33 rev times 60 seconds over 1 minute. Let's get the time it takes to do 1 rev. All right, I need a calculator. Let me see if I can get one here. Maybe I have one here. Let me look on my phone. Okay. All right. Calculator. Here we go. I get 1.81. 1.81 seconds. All right, so we have, let's see, 2 pi r. So we've got 2 times pi times 0.127 meters divided by 1.81 seconds. Let's see what that's going to give me. Clear. Clear code there. 2 times 0.127 divided by I get 0. Okay, so I get V equals 0.44 meters per second. That's my velocity, but now I want to do the acceleration. So A equals V squared over R equals 0.44 meters per second divided by R, which is 0.127 meters. That's going to be 1.52 meters per second squared. And it's directed radially inward. So yeah, so maybe go over this one a few times till you kind of master it. Okay, you drop a rock from a cliff and it takes 6 seconds to hit the ground. How high is the cliff? We've done this one a few times. So 10, we're going to use that x final equals x initial plus b naught t plus 1/2 at squared. So x final, that's what we want. We're going to call that 0, and we're dropping it, so that's 0, plus 1/2 times 9.8 meters per second squared. And it takes 6 seconds, so that's 6 seconds. That's quantity squared. The cliff is going to be 176.4 meters tall. So that's where we're at. It's 176.4 meters tall. Okay. A box is placed on an inclined plane. This is 11. That makes an angle of 60 degrees with respect to the ground, the coefficient of kinetic friction. So theta equals 60 is a mu k equals 0.04. What is the box's acceleration? So we've got m g sine theta, that's what it would be without friction, minus ff equals ma. So the in an ideal world without friction, we know that this component is mg sine theta, but that's this guy. But this guy is going to be the normal force times mu k. And the normal force is going to be, the normal force is going to equal to mg cos theta. So let's figure what we got out here. mg sine theta minus mg cos theta times mu k equals ma. Now are we, okay, so we don't need these m's. Okay, so we've got 9.8 meters per second squared times sine 60 minus 9.8 meters per second squared times cos 60 times 0.04. And that's going to be equal to, if you do the math, 8.46 meters per second squared. And once again, if you have any questions on any of these problem solvings, please come to the question and answer session, or contact me by email. Okay, I'm there. I'm here for you. Here to help you. You can watch these several times, and that will help. But if you still don't get it, then please contact me via email. All right, this is 12. It says 2 rods are made of the same wood. One is 10 centimeters, 10.0 centimeters, and the other is 5 centimeters, 5.0 centimeters. When the 10 centimeter rod is dropped on the floor, a sound of 88 hertz is heard. What will the frequency be? What frequency will be heard when the 5 centimeter rod is dropped? Well, V equals F lambda. We're going to hold V the same because that's a function of the temperature. So if I've got double my lambda, or 1/2 lambda, I'm going to hear double the frequency. So if we have a V equals F times 1/2 lambda, F is going to equal to 2F. I'm going to hear double the frequency. It's going to be much higher pitch. And that concludes, does that conclude it? Yes, that concludes our worksheet 6.